Welcome to our last week of the course. This week we are looking at diffraction. All waves diffract, but only when the aperture size is in the same order of magnitude as the wavelength. That means to look at diffraction effects, we need to look at very small apertures. You have already seen diffraction described as the spreading out of waves after passing through a small aperture. But more than just spreading out occurs, because the light will actually have an interference pattern that we call a diffraction pattern. This is the diffraction pattern on a screen produced by light that has passed through a single vertical slit. Diffraction caused the light to spread out perpendicular to the long sides of the slit. You see a broad central maximum, then you see that there are dark lines, so that the central maximum is surrounded by less intense and narrower side maxima. And diffraction isn't limited to narrow apertures like slits or pinholes. It also occurs when light passes a sharp edge, such as you get in a razor blade. This is the pattern you get when you illuminate a razor blade with monochromatic light. Just as with an interference pattern, you can see that there are lines of maximum and minimum intensity. And in fact, you can also get a diffraction pattern from a thin object. According to Babinet's principle, the diffraction pattern from a thin screen, so one tiny part of the light blocked, is the same as what you would get from a slit of the same width. The diffraction pattern at the bottom, you can see, is made from a single hair placed in the path of a laser pointer. You've already seen diffraction patterns like that more often than you may realize. If you look at a clear blue sky or a uniform light, you may see these funny patterns floating in your field of vision. What you are seeing is the diffraction pattern produced on your retina by light passing the edges of these tiny structures floating in the vitreous humour in your eyeball. Now for a little bit of history. At the beginning of the 19th century, Isaac Newton was dominating European science, and his particle theory of light was still widely accepted, even though Young and others were casting doubt on it. In 1818, the French Academy of Sciences launched a competition to explain the properties of light, where Poisson, a firm supporter of Newton's particle theory, was one of the members of the judging committee. The civil engineer, Augustin Jean Fresnel, entered this competition by submitting a new wave theory of light. Poisson studied Fresnel's theory in detail and looked for a way to prove it wrong. Poisson thought that he had found a flaw when he argued that one consequence of Fresnel's theory was that there should exist a bright spot in the shadow of a circular obstacle, where, according to the particle theory of light, there should be complete darkness. Poisson decided this was an absurd result, that there would be a little bright spot, and that should disprove Fresnel's theory. Unfortunately for him, someone actually tried the experiment, and sure enough, the spot was there. Fresnel won the competition, and Poisson was left with the embarrassment of having his name put to his most public mistake. This shows the danger of assuming the result of an experiment instead of actually doing it.